Alright, we're back and we're doing some more Biot-Savart. This time we'll do our second example with a current loop, which is acting like a magnet. This is a lot like the Helmholtz coils that we use in one of our labs with the cathode ray tubes at school. Over here is Biot-Savart for current. Okay, that's what it looks like to find a little bit of magnetism, a little element of magnetism being created by a little chunk of current going around the loop. And so from our picture, we're looking at the little element of current on the top of the loop. The direction of that is always going to be tangent to the circle at any given point. We have the total distance down from that current to a point on this axis coming right through the center of the hoop. So this is the one special case that we're doing where we have lots of symmetry to help us out. Now from the right-hand rule, we have to figure out what the direction of the magnetic field is out on the axis. So what's the r hat? Well, r hat is that little unit vector that points from the current down to where we're trying to find the magnetism. So r hat is along that radius line where we're trying to find the B field. Now, because it's a cross product, the magnetic field has to be perpendicular to both the current and r hat. So if you do the right-hand rule, you'll find that the magnetic field has to be perpendicular to this dashed radius line coming from the hoop. So it's going to point up at some angle like this. We'll call that theta right there. And so it's a 90-degree angle between the magnetic field and that dashed line, the radius line. So from the symmetry of all this, since we're on that middle axis, you also have current at the bottom of the hoop, which is going that way, and that's producing a magnetic field at the same location, only directed downward at the same angle. So if you think about this, you'd have like a cone of magnetic fields right there from all the different parts of the hoop. And all of the components are going to cancel out with the exception of the x components. Okay, the y's and the z's are all going to cancel. So we're only looking for the x components. So if we set up Biot-Savart, it'll look something like this. We have our constants, we have the current, and then dl cross r hat. Now that's all over r squared. Well, r squared is going to be a squared plus x squared. And to pick out just the x component, we have to multiply this by the cosine of that angle that's drawn there. Okay, so if we look at our big triangle, which angle is theta? It turns out that this angle up here has to be the same. You can prove it to yourself, do some geometry, but that's what our theta is going to be. And so I can substitute here for the cosine. We're going to substitute in a over r, adjacent over hypotenuse. Okay, so let me go ahead and do that. Okay, so once you have the x component from one little element of current, we can add up everything to get the total field that points along the x-axis. That makes up our integral. Now what's cool about this, and makes this actually, in the end, pretty easy to solve, is the fact that almost everything here is a constant. We've got the mu, the 4 pi, the current is just the number of amps. A, that's the radius of the hoop, that's a constant. And even x is a constant. It's a fixed point out on the axis. So when we pull everything out, we have 4 pi, and in our denominator we have the quantity a squared plus x squared to the 3/2 power. The integral just turns out to be this dl cross r hat. So that's really the only thing we have to try to figure out how to solve. And even that's not so bad in the end, because if we go back to our picture, the angle. Okay, we need the angle between the current and this r hat. Well, that turns out to be a right angle. So remember, to integrate a cross product, we need the magnitude. So we have all of our constants. Times the integral, we have our dl. The magnitude of r hat is just 1. And the sine of the angle between those two is 90 degrees, which is also 1. So if I erase those, really we're just left with the integral of dl. Well, what's that? Well, if we add up all these little pieces of length going around that circular hoop of wire, we just have the circumference, the total length of that hoop of wire. So our final answer, it turns out, at least on this axis, is mu naught times current times A. This integral gives us a factor of circumference, 2 pi A, all over 4 pi, oops, that's square root, sorry, times A squared plus x squared to the 3/2 power. And that turns out to be our answer. Okay, so again, that's all fine and good. That's just doing some math and working through this integral. The important part is how to set it up, back up here, using the Biot-Savart rule. We're looking at the geometry, we're getting the angles down, using this triangle to our advantage, and we're setting up this integral. In the end, we can get some answers out. So, I hope this helps, and until next time, take it easy.